So hi everybody, today I'm going to present you a new tool that I introduced and which is related to discrete surfaces and which makes us able to introduce what I call PCMs. I will detail after, but in brief, it is a poset-based combinatorial manifold. Okay, let's start. So the plan is the following. I will start with the introduction of the most used structures in discrete topology that we know. Then I will follow with the open question, which is if we look for a particular boundary which is discrete and at the same time does not depend on the ambient space, what can we do? I will propose a solution which I call border. We will see that there is a relation between this tool, this border, and what we call P-well-composedness and Recursive, which comes from mathematical morphology. I don't know if you know about mathematical morphology. It is a topic that we use in the LRDE at the EPITA for the tree of shapes, for example. You can ask me a question when you want. You can interrupt me, there is no problem. After that, I will speak about what I call n-PCMs and smooth n-PCMs, which are more constrained. Then I will see the main theorems that follow from these definitions of PCMs. And then we will see that we have additional properties of PCMs when we use the join operator. And I will conclude. So let's start with very usual structures that we know in topology. We have a topological manifold without boundary. We know that the topological manifold is a space where for any point in this space we can find a neighborhood which is homomorphic to Rn, in the case of dimension n, obviously. We have also the case of topological manifold with boundaries. When we have boundaries, in brief, we can know that there exists some points, for example, the blue point in this square. The blue point admits a boundary and then a neighborhood, sorry. And then it is in the interior of the manifold. And we have this point which does not admit a neighborhood which is more homomorphic to Rn, and then it is in the boundary of the manifold. Okay. We also have combinatorial structures like combinatorial manifolds. The concept is theoretically the same, but it is more complex to explain in some way, but let's try. The combinatorial manifold is a simplicial complex in which we can find points where the zero vertices admits either n-1 ball as link, and it is on the border, or n- sphere for the link, and it is inside the manifold. For example, in this case, you take the red point, you do the link in the simplicial complex, we see that it is a simple cluster. It means that it is an interior point. It is a one sphere. For this case, we have this red point, which is on the border. Indeed, when we compute the link in the simplicial complex, we see that it is a ball and not a sphere. So it is a member of the border. This configuration cannot happen in combinatorial manifolds because it is what we call a pinch. It is, we start from the red point, we compute the link, it is not connected, it is not n-1 sphere, it is not n-1 ball into the infinite. However, when you choose to study pseudo-manifolds, you can observe that we can have pinches. What is a pseudo-manifold? It is a simplicial manifold which is pure, as usual, where every simplex is a face of exactly one or two n simplices, and where x is n-1 connected. N-1 connected means that you take any 2 points, you can draw a path of n and n-1 faces between these two points. So this is the pinched sphere because it is a simplicial complex you can draw it with the n, where at this point, at this location, if you compute the link, you will have a triangle over there, a triangle over there, it is in 3D. A triangle over there, a triangle over there, and you will observe that it is not connected. So it means that this point is a topological issue that we call pinch. So it is a pseudo-manifold. Obviously, combinatorial manifolds imply pseudo-manifold, but the converse is not true. Now we have a more general set that everybody knows over there. I think it is posets. Posets, as you know, are supplied with an order relation, which is reflexive, antisymmetric, and transitive. Over there, we have the two spheres, the two combinatorial sphere, which is drawn using the ASO diagram. You have the two faces and their children. And in some cases, these posets can be called discrete surfaces. Discrete surfaces comes from discrete topology and mathematical morphology. The definition is the following. A discrete zero surface is a set of 2 points, 2 arbitrary points, which are not neighbors. And the definition of a K surface with K greater than 0 is that it is a poset which is connected and where any neighborhood of any point is a n-1 surface. For example, the two spheres represented as a diagram over there leads to this picture. You take the point C, you look for the neighborhood of C, so the parents, there are 2, the children, there are 2. You draw the neighborhood of C over there. It is a simple closed curve, so one surface. It means, since you can reproduce this operation all over this poset, that this two sphere is a 2 surface. It's okay for everybody? So we have seen discrete surfaces. We have seen, we could see that discrete surfaces do not have boundaries, but in fact we should define boundaries for discrete surfaces before and so on. We will see why there are no boundaries. It is why I propose to expose you the standard definition of boundaries, thinking that I look for a definition which is discrete and which does not depend on the organ space, at least. We know about topological boundaries. We know that they are the closure of a set minus the interior of a set. So the huge problem in this case is that it is the closure of a set in a bigger space E. So we can remove this definition. It is not what we are looking for. We have combinatorial boundaries. It is the same thing. They depend on an higher space. They are the intersection of the closure of 2 subspaces, but we still depend on the organ space. So we do not want this definition neither. However, there is another definition of boundary which is specific to combinatorial manifolds. If we take a combinatorial manifold, the boundary of C is a set of simplies whose link is a combinatorial ball. So we can see that we do not depend on the bigger space. This is the good point. We are discrete, but it is restricted to simplicial complexes. So we feel that it is not sufficient for us. How to extend to posets? We still are looking for a definition. We could use homological boundaries. We take a poset which is made of all these faces. I mean, you understand, this square contains this point, this edge, and this point, and so on. It is a part of a chemical complex. It is not complex. The homological boundary of this poset is the set of n-1 faces, which have only one coface, and you complete the closure of the set of n-1 faces. You obtain the set in red. The big issue is that it does not loop. And naturally, we want that this boundary loops. we continue to search. And then I propose to introduce a new kind of boundary that I call border, which will lead to this definition of border. It is not intuitive, I know. But the idea is that it is closed, it is discrete, it does not depend on the ambient space. So it seems to be what we are looking for. Just to compare, we have the homological boundary, the combinatorial boundary, and the topological boundary on this initial poset. So what do we do? For that, I have to introduce discrete surfaces in a rigorous manner. Sorry. To introduce discrete surfaces, I have to introduce the theta operator, and to introduce the theta operator, I have to introduce the order relation. I think the order relation is known by everyone. Theta operator is just the neighborhood. Theta square is the neighborhood of a point minus this point. Okay, and then we can define discrete surfaces like before. X is a -1 surface, sorry, if it is empty-order. A zero surface if it is the set of 2 points with non-neighbors. And like I told you before, n surface with n greater than or equal to 1 when it is connected, and when for any point, for any element, the neighborhood is a n-1 surface. For example, for discrete surfaces, because I think they are not very well known in your community, the Kalinski grid in ND is an n surface. Oops, sorry. No, so the definition I propose is the following. We can start from a poset X, or from 0 at least. We define the border as the set of points in this poset where the neighborhood is not a discrete surface. So I use discrete surface to define something more subtle than discrete surface. For example, how can we compute this border? I start from this poset. I take this face in red. The neighborhood over there is this point, and this point. We see it is not a zero, it is not a one surface, so it is this pixel belong to the border of this poset. I reiterate over there, over there, over there. We see that they do not look. In fact, they are simple closed, simple paths which are not closed. So for the other faces, the blue one, we can draw the boundary, the neighborhood, which is a simple closed curve. So it belongs to the interior of this poset, and this one belongs to the interior of this poset. The interior being the complementary of the border. At the end, we obtain what I presented before.
So basically, you're saying the border consists of all the points whose boundary is closed.
Neighborhood, whose neighborhood is not closed.
Whose boundary is not. Okay, that's very nice. Okay, yeah.
Yeah. So it is not very intuitive at the beginning, but we will see that under some constraints, we have many topological properties.
Yes, it's intuitive, right? Because this is saying that a point belongs to the interior if I have an open neighborhood around it. Right? It doesn't belong.
It comes from this idea that you cannot draw the neighborhood.
Yeah, exactly. Yes.
Yeah. Then, so I was telling it is not intuitive. It is because if you do not have a higher, greater space to include the structure, the border will not be necessarily closed. It can be disturbing. Closed under occlusion, because it is the usual relationship, order relationship that we use for posets, and the interior, similarly, will not be always open. However, we have many properties which are coming. We start from poset, and we take each an element of this border. We will always have this relation. This relation means that the border of the neighborhood is inside the neighborhood of the border in some way. In fact, it is the neighborhood of H in this border. I use this formula all the time in my proofs, so it is very useful. We have also another proposition which shows that it is not so, it is almost natural. In fact, this definition of border. If we take Y an n surface, that is a greater space which is a discrete surface, and we take X a poset in Y, when X is closed in Y, then the border is closed in Y. We get back, if you want, the property of closeness of the border. The similar formula follows for the interior, which gets back its property to be open. Okay.
What does it mean of rank n? It means it's a full dimensional subset.
Yeah.
Yeah.
So now the relation with mathematical morphology, because there is this one. In fact, what we call Alexandrov-composedness in mathematical morphology in a kind of regularity of a space, even if it is combinatorial, we have a form of regularity, which says that the shapes that are described in this space do not have pinches. I vulgarize. But what I mean is that the tree of shape exists on discrete surfaces under some prediction. We have also to be incoherent, but let's forget. So what I mean is that a poset X is Alexandrov composed when its combinatorial boundary is a separated union of n-1 surfaces. This is a very well-known condition that we need to have good properties in mathematical morphology to be able to build the tree of shape. In fact, we can do the relation with P-well-composedness. P-well-composedness is defines a set as being the border of a set is P-well-composed if it is a separated union of n-1 surfaces. It is almost the same thing. The proposition which follows from this is that if you take Y a discrete surface and you take X a subset of this surface, you can prove that the border that I defined before is equal to the combinatorial boundary that it is used in mathematical morphology. So Alexandrov-composedness is equivalent to P-well-composedness in this context. What I mean is that it is not so simple. From about 10 years, people using the tree of shape is using this kind of structure without knowing that it is this kind of structure. In fact, they are using PCMs without knowing it. They seem to use discrete surfaces, but they are on bounded domains. So they are not discrete surfaces. Okay, so let me introduce now the main tool of this talk. So I already defined the acronym PCM. The definition is the following. We'll see it is almost the same skeleton as for the discrete surfaces. -1 PCM is down order. The 0 PCM is a set of one isolated element. Only one element. The n-PCM is a connected poset where the border is not empty and where for any point of this poset, either you have a neighborhood which is n-1 PCM and then it belongs to the border, or the n-1 surface and then it belongs to the interior of this poset. For example, over there, I have drawn several possible, we can exist because it was easier, but we have several examples of PCMs. We will see that this one is a smooth PCM just after, and we'll see why. And we have a configuration that cannot happen on PCMs because if you take the point H at the center, you draw the neighborhood of H, you have this point, plus this point, they are the union of two n-PCMs, which is not connected. So the neighborhood is not connected, so it is neither PCM nor discrete surface because of from one. So you cannot have this configuration, which means that we have a kind of regularity in the discrete sense in this structure, which is very important and which allows us to define tree of shapes on it, in coherent space.
Explain again what's the poset structure that you are looking in your picture. So X is all these are posets, right? So all your pictures.
This one?
Yeah, so all these are posets.
Well, it is not a PCM?
No, so the poset structure, because you mentioned at the beginning that you work with a phase diagram, but then you have this picture. So
to explain the assay diagram of this picture.
Yeah, so how are you interpreting this picture as a poset?
So to draw the assay diagram of this picture, I could take this one, I put it at the level 2, and I draw that this edge is the child of this square, and these 2 points are the child of this edge, which is the edge, the child of this square. So we will have a point there, 2 points there. So it will be this connection like this.
Okay.
And I continue for all the.
Okay. Okay. Yeah.
Thank you for your question. So the topological properties, they are very basic. This one, in fact, the n-PCM being at the same time a PCM and surface is anti-order. It is very useful sometimes. When n is equal to 0, x is the poset of n0. Then x is a 0 PCM if we have only one element. If we have 2 elements which are not neighbors, it is a 0 surface. And if we have 3 elements or more, it is nothing in this context. When n is equal to 1, you take a simple path which is open, and we have at least 3 elements, it is a PCM, one PCM. If we have a loop, like I said before, it is one surface. And the border of a 0 surface and the border of a 0 PCM is the empty set. Always. It is normal in some way, but it's not so easy. Not so intuitive. And now the version plus of the PCMs, because we will see that there is an additional condition that we really need in practice. There are smooth PCMs, smooth in the discrete sense, obviously. -1 PCM as usual, 0 PCM as usual, but for the n-PCM, it means that it is in some way a smooth n-PCM is an n-PCM where the boundary, the border, is a separated union of n-1 surfaces. Okay? It is almost the same thing, and obviously it is stronger than PCMs, the standard PCMs. So it is a little proof that they are not equivalent. For those who are interested, you take just 2 points, which are neighbors. You have A, B, A parent of B. The border of this poset is equal to itself. And from this observation, we can conclude that the border, which is a PCM and not a n-1 surface, means that we have a poset which is a PCM, but not an n-PCM, not smooth PCM. It's just details, just to show that they are really different. For example, picture, we can observe that over there I have n-PCM, and over there I have a smooth n-PCM. The difference is in the border, because the border of this poset is all the poset itself. You see that it is not a discrete surface. However, in this case, you take this set, you complete the border, you have this piece of the poset, this other piece of the poset, you have the union of 2 discrete surfaces. You can understand that this is a separate union of 2 simple closed curves, if you prefer. Okay? And I will not detail because it's not very interesting, but the strong property of the smooth PCMs is that you have the border of the neighborhood, which is equal this time to the border, to the neighborhood of the border. The neighborhood in the border. So this property is equal in smooth PCMs. So not the main theorems, because the aim at the beginning was to do some tool which is useful to try.
So before you get to this, I have a question. So why do you call them smooth? Because
I know.
it looks like the property should be it's a closed, but it's a
Perhaps I should
use something else. I don't know.
Perhaps I should try to use regular. Or something else.
No.
But I wanted to make a parallel with the notion of continuous topology and to do a smooth like differentiable manifolds compared to manifolds. It is in this sense, but I know that smooth is not probably not the best term. But
it's
it's confusing.
In normal geometry, you don't really have this notion, right? Because
but
manifold with you have a manifold with boundary where some of the boundary is missing in a sense, right? Then it would be not smooth in a sense. I don't know. Okay.
I know we can be disturbed by this term. Perhaps that we are changing. So the main theorems are very intuitive. At the end, you imagine that you have two n-PCMs which have the same border. We have some additional conditions which are very natural. For example, we have not an overlapping, a strange overlapping of two manifolds. We imagine that they are separated, but at the level of their border, their border is equal. Moreover, the intersection of the two PCMs is equal to the border of each one. It is completely natural. When we do this union, we obtain a discrete surface. It is very related to what we look for in continuous topology. We have another theorem, which is in some way the converse. The question is, we take a sphere in the sense poset, which is a smooth n-PCM. We cut this sphere everywhere with an n-1 surface. We will obtain either one component, for example, a torus. If you remove the handle of a torus, it is still one component. Yes? No, just pass away. Okay, if you have one component, it means that we have a torus. We have removed a cycle which does not separate the initial space. And when we get back this border, we get back the initial poset. When we remove this discrete surface of dimensional -1 and we have two components, there will be, when we get back the border on each one, two smooth n-PCMs. And the case of cardinality equal to 3 or greater is impossible. It's simple. So it is the converse of the previous theorem. And there is another, which is kind of maze for me, because in fact, if we take two smooth PCMs this time, and we just try to overlap one PCM over the other one, and the shared part, for example, over there, is still a PCM, of dimension n-1, the union will be not a smooth PCM, but a PCM. I didn't succeed for the moment in proving that the union of two n-PCMs can be, when they are smooth, a smooth PCM. However, I proved that two smooth PCMs lead to a PCM. I really tried. After 3 or 4 pages of computations, I was thinking I will see later. So it is an open question. However, if you do the overlap of the two PCMs and the intersection is not the n-1 PCM, you will have, for example, a pinch overlap. The pinch means it is not PCM, it is not real. I do not develop the different positions because you will see that they are more complicated to understand than to imagine because they are very natural. In fact.
So the overlap cannot be too small, like
Yeah.
you just said, but it cannot be too big either because the intersection needs to be not more than the intersection of the border.
The intersection needs to be a PCM.
Yeah,
Smooth PCM.
And this first condition says the intersection of A and B is the intersection of the borders of
Yeah.
of A
Yeah,
and B.
yeah,
So
yeah,
you
yeah.
can't have too much overlap.
Yeah, indeed, if you have an overlap which is from 2, in this case, it is not a one PCM, it will fail.
Yeah.
Obviously, if you do the union of the two initial spaces, it will work, but it is not interesting. So the one question is, when do we have a union which leads to smooth PCM? And for the moment, I'm not able to say it. I have also some additional properties to show. We know that for discrete surfaces, when you do the join of two discrete surfaces, it is still a discrete surface. The question is it true with this PCM? For example, just to get back to discrete surfaces, you have a zero surface, join with zero surface, you have a one surface, which is corresponding to this simple cluster, or this one sphere. You take the zero surface, you join with one surface. You have these two surfaces, these two spheres, and so on. So this property of joining, preserve discrete surfaces. In fact, this is true for PCMs almost. In the sense that if you do the join of a surface and a PCM, it is a PCM. If you do the same thing with a PCM and a surface, it is still PCM. The join operator is not symmetrical. And we know the values of the boundaries. So the conclusion, we have introduced a new kind of boundary that I call the border to differentiation reasons. We introduced a counterpart of discrete surfaces, but with the border. We proved three theorems relative to PCMs, and we have shown that PCMs have also properties with the join operator. So the following, the future works, is to answer to the question presented before, and to find additional properties for PCMs. Thank you for your attention. Do you have questions?
Yeah, thank you very much. So what about questions? I'm staying sitting because I have some notes. Any questions?
Did you understand a little about this too? It is my question, my fundamental question, because I know it is strange.
I think your question was very good, right? Because it's not obvious for everybody.
Yeah,
what
yeah,
is a
yeah,
poset representation.
We introduced from the geometrical to the actual diagram. I know it's not at the big.
Yeah, I was in.
It's my fault.
Yeah, but no, it's fine because it's like how you are representing your mind the poset. So these geometries are these new geometries are
You can be
a structure that
anything.
you don't to a regular poset at least.
I think it's obvious to think of like this for image analysis people because
No, neither.
Neither. Okay. So I have a question about the join.
Yeah.
So I did not understand the second join you were showing. This is on slide number 36. Because I'm interested in this kind of one before. One before there was an example. The
okay.
join of a discrete thing EF with the result of the composition above. Why doesn't it look like this?
Okay. The definition of the join operation is that you have a first relation in this of conclusion if this poset. You have a second relation is this poset,
yeah.
And the relation of the join of the two posets is in fact the union of the order of this one with the order of this one with the Cartesian product of the one you put at the top, in this case, this one, with the other ones.
Yeah, this is what I call the serial composition of posits.
Yeah, I remember I saw the link. Yeah,
Yeah, I remember. Yeah. Okay, and now I see, yes. So E and F are above. I did not see the, okay. And they are related to everything else. And now why is this a sphere?
Oh, in fact, we can draw it as a sphere. If we, I think also that it is the smallest sphere we can draw in combinatorial settings. Why it is a sphere? Because you have E, which has these two child, C and D, which are one faces.
Yeah.
So you can consider that C and D are the edges of the boundary in some way of the two faces.
Yeah.
We have also A and B, which are closing C and D. They are shared between C and D, so we can put them over there and over there. And that's all.
Yeah. Okay. So if I take another joint with a discrete poset, then I get a fourth sphere, right?
But
or a three sphere.
This picture comes from David Aragon, which makes his thesis on posets and on the chain complexes, but not at a homological point of view, as subdivisions, in fact. So there are many of these pictures. Some are very nice in this thesis, if you want. But indeed, we can imagine that we can do isomorphisms to start from one representation to another completely different representation. It has something which is arbitrary.
Yeah, of course,
So the way that I interpreted that is that if you think about the picture in your right and CW complex, and
Yeah,
look at the inclusions of the cells.
They are CW complexes.
Yeah. So the inclusions of the cells is about possible. So.
But I think there are many posets that we cannot represent for homological purposes. Sure. Okay. Yeah.
A word that I missed. Sorry, we should talk about this. But do you know that the order complex of PCM is a kind of simplicial combinatorial manifold in whatever sense?
Oh, wait. If you think about the combinatorial maps, I am totally lost. I don't know almost at all. I know there are NG maps and so on, but there are NG maps, combinatorial maps, and so on. There are different kinds of maps, but I don't know where about them. But perhaps I did not understand the question.
I know. So if you take the PCM and you take its order complex, so that's simplicial complex, and you started talking about kind of simplicial combinatorial.
Yeah, but it is not always simplicial. But you mean if it is simplicial and PCM at the same time?
No, I mean that if you take poset, you can always take the order complex of that poset, right? And that's a simplicial complex.
I don't know about order complexes, which could explain what I is.
Also, sorry, but this is so you're asking if you're taking this also, but then you take the other complex, if this is the regular or if this has some relationship between the boundary of this complex.
No, I'm just asking. I'm literally asking if because I guess there are kind of these kind of simplicial versions of what combinatorial manifold is. I was just wondering if taking the order complex takes this kind of form of combinatorial manifold into the simplicial combinatorial manifold.
But you can transform any complex, any poset in a combinatorial in a simplicial complex by the very simple subdivision, for example.
I mean, I guess percent subdivision is the same as order complex. So yeah, that could be also like it's percent subdivision of a PCM, a kind of a combinatorial manifold in a simplicial sense. Sorry.
So I don't know about order complexes either, but it seems to me like, so for example, just looking at this example, if you take the order complex of the first one, right, it's something which looks again like a circle, but very differently because now you have 4 pieces which
Oh, yeah, absolutely.
stick
But there's
together. So I'm really wondering whether there is any relation between this surface and its poset representation and then the order complex of the poset representation.
well, there are some like, I mean, well, if you take regular CW complexes and then you take their phase poset,
Yeah.
and then you take the order complex, so that's phase poset. Actually, they are that's homeomorphic.
Okay,
So there are
Okay.
definitely good cases in which the two things
Yeah,
are very
yeah.
strongly the same.
Okay. Okay.
And well, these are in particular regular CW
Yes.
complexes.
Yeah.
So
Mhm.
it's a case in which you would have a homeomorphism.
Okay. Thank you. So yeah, let's finish this. Let's think Nico once more. Yeah. Just about 20 minutes to get back to